Okay, this is auto playing this doggy. Introduction to Deep Reinforcement Learning. So this is Unit 1. Welcome to the fascinating topic of artificial intelligence. There's a dog in the background. Welcome to the most fascinating topic in artificial intelligence, Deep Reinforcement Learning. Deep RL is a type of machine learning where an agent learns how to behave in an environment by performing actions and seeing results. In this first unit, you'll learn the foundations of deep reinforcement learning. Then you'll train deep reinforcement learning agent, a lunar lander, to land correctly on the moon using stable baselines 3, a deep reinforcement learning library. Great. So we have access to these environments. Here's a landing. Great. Yeah, this is nice. So you'll be able to, interact with this world and probably have some controls going left, going right, or maybe just accelerating, decelerating. Finally, you'll upload this trained agent to the Hugging Face Hub, a free open platform where people can share ML models, datasets, and demos. Great. So, just like GitHub, you will be able to create your own model and post it to Hugging Face Hub. It's essential to master these elements before diving into implementing deep reinforcement learning agents. The goal of this chapter is to give you a solid foundation. This is perfect. So you have this lunar lander landing on the moon. After this unit, in a bonus unit, you'll be able to train Huggy the dog to fetch a stick and play with him. Okay, so fetching a stick requires, moving all four legs, using your mouth, grabbing the stick. Perfect. So what is reinforcement learning? To understand reinforcement learning, let's start with the big picture. The idea behind reinforcement learning is that an agent will learn from the environment by interacting with it through trial and error and receiving rewards. Okay, so interaction, trial, error, and receiving rewards. Learning from interactions with the environment comes from our natural experiences. For example, imagine putting your brother in front of a video game he never played, giving him a controller, and leaving him alone. Your brother would interact with the environment, the game, by pressing the right button, action. He got a coin, that's a +1 reward, that's positive. He just understood that in the game he must get the coins. Okay, great. So I think there's some idea as a human in a biological sense that there are rewards that you want. In games there are side missions, there are coins, and there's actually winning the level. So there's probably some hierarchy to rewards that we talk about later. But then he presses right again, he touches an enemy, he just dies, so that's a -1 reward. Right, so, using your own perception, you know what's good and what's bad, and typically when you encounter a bad thing, you try to stay away from it. By interacting with the environment through trial and error, your brother understood that he needed to get coins in this environment, but to avoid enemies. Without any supervision, the child would get better at playing at the game. That's how humans and animals learn, through interaction. Reinforcement learning is just a computational approach of learning from actions. So it's interesting that they say without supervision. From my thought, supervised learning is when you have labels. Unsupervised learning is when you do not have labels, and typically that's used for clustering and grouping tasks. Here, I feel like +1 and -1 are labels, right? It's for telling it what it should want, what it should not want. And to be honest, if I give my little brother a game, he might not do the thing that I expect him to do. He might just try to run around, he might just try to figure out what game dynamics the game has so he can get better at the game in the future, or just exploration. So I think this analogy breaks down. If you actually if you actually had a little brother, typically they will not do the thing you expect them to do. They have their own internal sense of reward. But for the sake of this article, that's let's forget about that. So formal definition. Reinforcement learning is a framework for solving control tasks, also called decision problems, by building agents that learn from the environment by interacting with it through trial and error and receiving rewards, positive or negative, as unique feedback. Perfect. So there's a formal definition. I don't know why it says unique feedback. Anyway, great. So the reinforcement learning framework. So this is the RL process. You have an agent. They take some action inside of this environment, and the environment will give a reward or not reward back to the agent and send a new state back to the agent, right? So you can decide to, take one step down a flight of stairs, and the environment with gravity, with friction, with what your shoes are, with, everything will give you the next state of the world, and then maybe it will give you some reward. Are you getting closer to your goal? Are you getting further from your goal? The RL process, a loop of state, action, reward, and next state. So this is from a book called Reinforcement Learning Introduction by Sunit Barto. Great book. We will read it in a different video. To understand the RL process, let's imagine an agent learning to play a platform game. So the agent is this main character. The action is here are the available actions, and they zoomed in on this right click. The environment is maybe an enemy, and here's the state. The agent receives state 0 from the environment. We receive the first frame of the game. Based on state 0, the action takes action 0. Our agent will move to the right. Environment goes to state S1, which is a new frame, and the environment gives some reward. Here R1 to the agent. We're not dead, and that's a positive reward, +1. So in this environment, just being alive is a positive reward. This RL loop outputs a sequence of state, action, reward, and next state. Right, so state 0, action 0 goes to reward 1, state 1. Right. The agent's goal is to maximize its cumulative reward, called the expected return. So we're just trying to max cumulative expected reward. Okay, so that's a key word. Expected reward. Expected return. Great. So the central theory, the reward hypothesis, the central idea of reinforcement learning. So the reward hypothesis. Why is the goal of the agent to maximize the expected return? Because RL is based on the reward hypothesis, which is that all goals can be described as the maximization of the expected return, expected cumulative reward. So I think there's an idea that there's a scalar value, and we're just trying to maximize that scalar value. This is the optimization problem to maximize that number. That's why in reinforcement learning, to have the best behavior, we aim to learn to take actions that maximize the expected cumulative reward. So the Markov property. In papers you'll see that the RL process is called the Markov decision process. We'll talk again about the Markov property in the following units, but if you need to remember something about this, it is this. The Markov property implies that our agent needs only the current state to decide what action to take, and not the history of all states and actions they took before. Now this is confusing to me when I first read it in the past, but I think the idea is that the current state, imagine like where you're sitting right now, what you're doing right now. The action that you're going to take is dependent on the current state. Now, does that mean that you have no knowledge of the past? No. The state of your brain is part of the current state, right? The state of your body is part of the current state. The state of your memories is part of the current state of your memories. As you grow older, the memories decay. As your brain function decays, your memories might disappear. This is your current state of the world. This is not to say that the history doesn't matter. In fact, in a lot of RL, we need to accumulate some, embedded version of the history, because history does matter, right? If a ball is coming to me, but if you take one picture of the frame, the ball is just floating in the air, you don't know which direction the ball is going towards, right? But that's not to say that the history of that ball doesn't matter. It matters, but we have some memory of the trajectory of the ball, where it came from, and that is still part of the current state. So that was the thing that confused me a lot when I first looked into this. So observations, state space. So observations and states are the information our agent gets from the environment. In the case of a video game, it can be a frame, screenshot. In the case of a trading agent, it can be the value of a certain stock, etc. There's a differentiation to make between observation and state, however. State is a complete description of the state of the world. There's no hidden information. In a fully observed environment, so like this, in a chess game, the state is all the pieces on the board, right? And if this was a simulated one-on-one chess, environment, then the full state is, not only the pieces on the board, but maybe my opponent, what my opponent had for lunch, how they feel, their state of mind, like maybe that's also part of the state, right? In a chess game, we have access to the whole board of information, so we receive a state from the environment. In other words, the environment is fully observed. Right? An observation is a partial description of the state. In a partially observed environment, like here in Super Smash Bros., we only see part of the level close to the player, so we receive an observation. Right here, we only see part of the level. And not only do we see part of the level, but we don't see the parts that are unseen to us. Right? So what's in this question mark? I have no idea. What's in this question mark? I have no idea. But the game state knows exactly what this is. It's somewhere in the game state. But as a player, I only observe certain things about it, right? If you play any video game, or if you know any, if you played any video game, there's an idea that you don't know all of what's going on. But you can observe what's going on, and you can make decisions based on what you can observe. And you can imagine that if we're building an agent, it's only going to be able to make decisions based on its observations. So in Super Mario Brothers, we only see a part of the level close to the player, so we receive an observation. In Super Mario Brothers, we are in a partially observed environment. We receive an observation since we only see part of the level. In this course, we would use the term state to denote both state and observations, but we will make the distinction in implementations. So to recap, the observation state, right? Complete description of the state of the world, no hidden information, versus observation, partial description of the state of the world. The action space. The action space is a set of all possible actions in an environment. The actions can come from discrete or continuous space. Discrete space, the number of possible actions is finite, right? So, discrete space, we have a finite set of actions since we only have 4 directions, and jump, right? Up, left, right, and down. We can jump. Realistically, I think we can also hold B and we can sprint. So left and right can be faster. So this is a little bit wrong, but for the sake of the course, it makes total sense, right? This is discrete actions. Continuous space, the number of possible actions is infinite. So a self-driving car agent has an infinite number of possible actions. It can turn left 20 degrees, 21.1, 21.2, honk, turn right, 20. There's the space of what you can do is, at least an immediate action, is infinite, or So taking this information into consideration is crucial because it will have importance when choosing the RL algorithm in the future. Rewards and discounting. The reward is fundamental in RL because it's the only feedback for the agent. Thanks to it, our agent knows if the action taken was good or not. The cumulative reward at each time step t can be written as R of t, where it's R of t plus 1, R of t plus 2, R of t plus 3, R of t plus 4. You add all of those together, right? So it's every reward towards infinity. However, in reality, we can't just add them like that. The reward that comes sooner at the beginning of the game are more likely to happen since they are more predictable than the long-term future reward, right? So if I give you $1 today versus I give you $2 in 10 years, which option would you take, right? Am I going to be around in 10 years? Would you still have my number? How much do you need that dollar today? What if I gave you $100 in 10 years, right? Would you take the dollar today or the $100 in 10 years? Would you take the dollar today or $1 million in 100 years? Now you may want to take the $1 million in 100 years, but I might not be alive, and might not be here to do the deal. In fact, you might not be alive. So there's an idea in a lot of these, sum of return, sum of reward ideas that the earlier the reward, the better, right? And this flows directly to how people model financial instruments, right? The returns earlier are more valued highly, and that they are discounted into the future because the future reward needs some discount factor based on how unlikely they are to occur. So let's say your agent is a tiny mouse that can move one tile each time step, and your goal is the cat, and your opponent is the cat that can move too. The mouse's goal is to eat the maximum amount of cheese before being eaten by the cat. As we can see in the diagram, it's probable to eat the cheese near us than the cheese close to the cat. The closer we are to the cat, the more dangerous it is. Right, so this is under the assumption that the cat will eat the mouse, so the mouse has to stay away from the cat. Consequently, the reward near the cat, even if it is bigger, will be more discounted, since we're not really sure we'll be able to eat it. To discount rewards, we process like this. We define a discount rate gamma. It must be between 0 and 1, most of the time between 0.99 and 0.95. The larger the gamma, the smaller the discount. That means our agent cares more about long-term reward. On the other hand, the smaller the gamma, the bigger the discount. This means our agent cares more about short-term reward. Then, each reward will be discounted by gamma to the exponent of each time step. As the time step increases, the cat gets closer to us, so the future reward is less and less likely to happen. Our discounted cumulative reward is, this factor, right? So this is the same equation as above, except that it's multiplied by some discount rate, right? Here's gamma. And in the previous, they said it was 0.99 or 0.95 is a good amount.